Okay, now let's dive deeper into differential and integral calculus. Okay, so what is it that we're going to look at? Remember when we looked at pre-calculus, we were almost always looking for a single point. So we would say maybe A is equal to 1, B is equal to 2, C is equal to 3, but usually these would still be a single point. These would be maybe 3 dimensions or something like that. The most important thing to understand here was that there was no change associated with what we're doing. There was no relativity. We would find A, B, and C, but would not find the relationship between these. Okay, would also not find the relationship between these and time and things like that. Why? Because first, our eyes can't just look at, let's say, a graph like this, and then be able to calculate this area here, for example. Or we can't look at something that's moving, okay, that's moving, and then be able to define the relationship of this with respect maybe to another. Or could be the motion of this with respect to time. We'll not be able to tell those with the concepts we have in pre-calculus. The main reason is that we have, these usually happen at a point that we earlier on called undefined. Or sometimes we said it was indeterminate. Okay, so calculus tries to find ways around that. Right, so what is the major concept that is related to calculus? The major concept that is related to calculus is change. Now, some will tell you that it's about motion. Yes, motion is change because a particle or let's say a vehicle is changing positions. So that is change. So calculus is mostly related to change. Okay, so what are the two main aspects of this change? The two main aspects of this change could be the rate of change when we look at time. Okay, so relative to time, if something is changing relative to time, we'll say it's rate of change. It could be speed, it could be velocity, it could be anything that works against time, okay, or with time. Now, we can also look at relative change. This is another concept. What is relative change? Relative change would be, for example, I'm looking at a change in y versus the change in x. I'm not talking about time in this case. I'm just looking at the relation between these two in terms of change. Okay, so we find these applications. We have, we can find that in motion. We can find in a number of series. Let's say you're looking at decay of a particle or radioactive substance and stuff like that. So you are going to have some form of change there. So we can still use calculus. Now, there are two main areas of calculus. What are these areas? We have differential calculus, and then we have integral calculus. Now, what we need to understand is that these are actually just opposites of each other. I think that is the first important principle that we need to understand. These are actually opposites of each other. Okay, so when we're talking about differentiation or differential calculus, we're mostly talking about mostly talking about derivatives. Okay, this is what we're mostly talking about. So differential calculus, or it deals mostly with change. Like we said, the change is represented like this, where we're saying dy dx. Okay, or some can say dy like that, x. So changing this over changing that. And also the change can be against time. And you can actually find a relationship in this case when you have a relationship against a common element. So here the common element is time, meaning that I can find the relationship between y and x, the change in y versus the change in x, if I've got the rates of the two. Right. Now, we use differential calculus mostly to find change. Okay, it's not the whole calculus that is focused on change. The primary concept in calculus that is focused on change is differentiation. Okay, so differential calculus or derivatives These are focused on change. Now, if we look at integral calculus, it's the inverse. So if we're looking at change, what will this other one look at? It will look at no change, something that's static. Okay, so we are moving from more change to less change. That is what integration does. Now, these are simplistic definitions we'll define deeply as we go. Why am I saying that calculus looks at, integral calculus looks at change to little change or to no change? Let's say I've got distance here. Okay. If I came and differentiated distance, okay, what do I get? Let's say I've got distance as s, okay, displacement, right? So I'll have ds over dt. So this one will give me displacement or distance, okay? And what will this one give me? Because this is displacement, this one will give me velocity, not speed, because we have direction now, okay? And what will, if I went to the second derivative of this one, okay? Imagine I'm differentiating downwards, right? So this one is the second derivative. This one will give me what? Will give me acceleration. Okay, so I'm differentiating downwards like that. But if I came and integrated this, now acceleration, it's second derivative, there's more change here. But if I went and integrated this, I'll get velocity, which has less change. Then if I integrated this as well, then I'll get what? Distance or displacement. Meaning that here there's it's more static than this one here. So that's why we're saying that this is the inverse process of differentiation. And the good part about it is that as we are going up, as we are integrating, we're actually going to look at the amount of something. Here we're looking at change. Okay? Change in the amount of this something. But if I go back, I'm going to settle at the amount at that point. Okay, so we're looking at the amount or the quantity of this variable. Now, most application, you find that you're calculating an area that will represent something. So this area could represent velocity, that area could represent distance, or you could actually do volumes. So for example, if I calculated that area, depending on what this is, if this is velocity, then this will be distance here. If this is acceleration, then that will be velocity. Something like that. So this is very important to understand. Now, the key thing that we need to settle with now as we begin is to say that now this is a lot of material. Okay, it's a lot of material if we look at it. Now, what is our starting point? What is the best place to start from if I were to understand this deeply? Okay, the best place to start from is to start by understanding differential calculus. If we want to understand differential calculus, we have to understand derivatives. Okay, and how do we understand derivatives? I think the best way to understand them, that is just an opinion. There are several ways you can understand this, but I feel that the best is to look at the limit definition of derivatives, and then you look at the rules. Okay, but not all the rules at first. You have to understand the power rule first. Then the power rule splits into everything else. Okay, so again, you start with limit definition of the derivative, and then you also go in and understand the rules of differentiation. Could be the sum rule, quotient rule, and all that. But we're going to focus on the power rule first because that is what links everything together. So let's begin by looking at the limit definition of derivatives. So we are looking at derivatives. Why are we looking at derivatives? We're looking at derivatives now to understand differential calculus, and then we'll understand integral calculus. Once we understand those two, then we've understood calculus, with obviously the pre-aspects that we looked at, like limits and other things. Okay, all right, all the best.